We're going to start with separating mixtures. We're not going to do solid, liquid, and gas because if you don't know what it is, then you're already cooked. So just don't worry about that. So to begin with, we have simple distillation, which is this diagram here. This is to separate a liquid from something that's dissolved in it. In this case, we have salty water. So distillation is when you boil the water and then you condense the water again through this tube into a new cup. So that should just leave your salt in the original beaker and your pure water in the new cup. Fractional distillation is the exact same thing, but it's just two different liquids. In this case, it's water and ethanol. So you'd boil the ethanol, because that boils at 78 degrees, which will leave just water in the original, and then the ethanol in your new beaker. And there's filtration, which is pretty straightforward. You have a solid in your liquid, so you put it through a filter funnel, and only the liquid should pass through. And lastly, we have crystallization, which is very similar to distillation. So you have something dissolved in a liquid, and you heat it up until the liquid evaporates. The only difference is you do not condense it and collect the liquid later. You just leave the liquid to evaporate, and then it's just gone. And then the crystals will be left behind. So it's similar to distillation, but you do not collect the liquid afterwards. So this is paper chromatography. Um, Again, we have the whole setup here in this image. You can see. You should draw a line with a pencil, and then put different types of inks on that pencil line. Once you dip it into a solvent, those dyes should all rise up the paper. You can see here in this diagram, for example, this black dot became red, yellow, and blue. So this just shows that this black dot is a mixture of all three of those. And you can see the red dot stayed as just a red dot, which shows that it's a pure substance. There's nothing else mixed in it. So here's a bit more of a zoomed in diagram. The main thing you need to know is how to calculate the RF value, and that is how far does the solvent travel up, divided by how much the substance traveled up. So they'll give you like two numbers. Just divide a small number by a big number, and you'll get it basically every single time. There are three steps to make drinkable water. The first step is filtration, where you filter out all of the solid particles that are in the water. The second step is sedimentation, is when all of the other particles gather at the bottom of the tank. And the final step is chlorination, where you add chlorine to kill all of the bacteria. So you guys should know what an atom is and what protons, neutrons, and electrons are. I'm not going to say anything about it because, again, if you don't know what they are, then it's already over for you. So don't worry about that. But an isotope should be an atom with the same number of protons but a different number of neutrons. So you can see here there are two isotopes. They both have 37 protons, but a different number of neutrons. So you need to find the relative atomic mass, so the mass number that you'd find on the periodic table. So to do that, you need to multiply the mass number of the isotope by the percentage of the isotope. In this case, 37, that's like 85 times 72. And do the same for the second isotope. So that would be 87 times 28. Okay, it's really bad. I'm using a touchpad. But yeah. You have to add up your answers and just divide it by 100. And that would be like 3 or 4 marks just from doing that. So mass number times the percentage, mass number times percentage, add them up and divide it by 100. So periodic table is over here. You can see it with your eyes. Each group tells you how many electrons it has in the outer shell. For example, in group 1, all the group 1 elements have 1 electron in the outer shell. Or in group 7, every element in group 7 has 7 electrons in the outer shell. And the original periodic table was made by Mendeleev, and he had to leave gaps because all the elements weren't discovered yet. And when he discovered new elements, they were able to fill in those gaps, which proved that his periodic table was correct. All right, this is probably gonna have to lock in because it's gonna be a little bit long. But honestly, if you know this is like half the paper to be honest. So just focus for 5 seconds. So there are four types of substances. We have ionic compounds, simple molecules, giant covalent, and metallic. You need to know the structure of all of them and also their properties as well. So we're going to start with ionic compounds. Ionic compounds are made of metals and nonmetals. So the metal will donate its electron to the nonmetal. So then the metal will now become a positive ion, and the negative ion is going to be like the nonmetal because it gained an electron, right? So because the ions are positive here and negative over here, they will be attracted to each other. The attraction between like a positive and negative thing is called electrostatic attraction. So an ionic bond means electrostatic attraction between the positive and negative ions. The properties that they have was A, it will have a high melting point. This is because you need a lot of energy to overcome this electrostatic attraction. Another property is it can only conduct electricity when molten or aqueous. So if it's solid, it cannot conduct electricity. This is because the ions can't freely move. So you need to have things freely moving to conduct electricity. The next part is simple molecules. So as you can see, these molecules are quite small compared to that giant ionic thing, right? So there's no like positive, negative, none of those forces. The only force there is weak intermolecular forces between them. So examples of a simple molecule would be put any non-metals together. For example, I know water, that's H2O, or O2, or anything that's non-metal. They will be a simple molecule. So they have a low boiling point because they have weak intermolecular forces, and they can't conduct electricity because there's no free moving like ions or electrons or anything. So yeah, but that's all the properties you need to know about simple molecules. Metals, the structure looks like this. So it's a bunch of positive metal ions and a sea of delocalized electrons. They have a high melting point. Again, this is because the strong attraction between the positive and negative needs a lot of energy to overcome. Another property is they can conduct electricity. This is because they have the free moving electrons, so they can carry the current. They are malleable, meaning if you hit a metal, it will bend or change shape. And those are the properties of metal that you need to know. Now, the final one is giant covalent structures. So, the examples of that you need to know are diamond, graphite, and silicon dioxide. So, here's an image of diamond. Diamond is only made of carbon atoms. And in diamond, each carbon is bonded to four other carbons. So, you can see here, each that carbon there is bonded to four other carbons. They always, like every giant covalent thing, will have a high melting point, and it's because it has strong covalent bonds. Diamond specifically is hard, and it shouldn't conduct electricity, so it doesn't conduct any electricity. This is because there's nothing free moving, no free moving electrons or ions, so it should not conduct any electricity. So just like diamond, graphite is also just made of carbon, but the main difference is each carbon is only bonded to three other carbons, whereas in diamond, each carbon is bonded to four other carbons. So the main properties you need to know is it can conduct electricity. This is because it has delocalized electrons. It's also soft, and this is because the weak intermolecular forces between the layers means it's very easy for them to slide over each other. A singular layer of graphite is called a graphene. So here's the pH scale, and hopefully you guys know what this is. So from 0 to 6 is acidic, and then 8 to 14 is alkaline. But what does that even mean? You know, what does an acid mean? What does an alkaline mean? That's the two very important things. So an acid is something that releases H plus ions when it's dissolved in water. An alkaline is something that releases OH minus ions when dissolved in water. And you have to use an indicator to see the pH of something. For example, a universal indicator could show you if something's acidic or alkaline. So if something is pH of like 1, that means it's a stronger acid than something that's pH of 3. But numbers wise, it means every time you go down by 1 pH, the number of hydrogen ions times by 10. So every time you go down 1, your H plus ions will go like times 10. So that's what shows it being like a stronger acid. Now, the only acids you need to know about are sulfuric acid, hydrochloric acid, and nitric acid. But when it comes to bases, it's kind of hard to realize if something's a base or not. So the way to figure that out is just look at the names of the alkalis. So alkalis are always some kind of metal, oxide, or hydroxide. I know I've been saying alkali and base kind of interchangeably, but if it's soluble, we have to call it an alkali. If it's insoluble, we call it a base. That's the only difference. But yeah, an alkali should be able to neutralize an acid. And you can see here, when you put in water, it releases OH minus. So this is what makes it an alkali. So any metal oxide or hydroxide, that is an alkali. So this is the neutralization reaction, where you react an acid with an alkali. And this is the general format it should look like. So you should make a salt and water. The salt depends on what acid you're using. So if you're using hydrochloric acid, it will make something chloride. If it's sulfuric acid, it's something sulfate. And nitric acid will make something nitrate. For example, hydrochloric acid and sodium hydroxide should make sodium chloride and water. Similarly, if you say a metal carbonate instead of sodium like hydroxide, if it says sodium carbonate, the only difference is you have to put carbon dioxide as well. So I'd make sodium chloride and water and carbon dioxide. You have to add that on as well. So there are tests that you can do to make sure the gas is being produced. This is the hydrogen test. So you have to light a splint and there should be a squeaky pop. Carbon dioxide will make lime water milky. Lastly, we have the practical, which is making a salt. So you should know that you make salt when you do neutralization reaction. So in this case, we are reacting, normally it's copper oxide, and we're reacting it with hydrochloric acid. So you'll keep adding the copper oxide until it's fully reacted, until it's in excess. You then want to filter out that excess that you put in to make sure that there's no solid parts in your solution. If you remember, when you react a base and a acid, you should make a salt and water. So in the case of copper oxide and hydrochloric acid, you should make copper chloride and water. So this copper chloride mixed in water is going to be our solution here, this blue solution. You then want to heat up until the water evaporates, leaving just copper chloride crystals, and you have to leave that out to dry. So this is an example of crystallization. So again, it's the products of reacting a base and an acid. We just have to crystallize, we have to just filter and then crystallize it so we can get our salt at the end. And again, the general example is copper oxide and hydrochloric acid to make copper chloride. But they could ask you to make copper sulfate, for example, which would be copper oxide and sulfuric acid. So any salt they can ask you to make. Electrolysis is using electricity to split up an ionic compound. In this example here, we have sodium chloride, and it's being split up into sodium ions and chloride ions. Your positive metal ions should be going to the cathode because the cathode is negative, and your negative chloride ions will go to the anode. Again, here's an image of another example. This time it's lead bromide. So our positive metal lead should go to the cathode, and our negative bromide ions should go to the anode. And you can see in these diagrams down here, once our positive lead ion goes to the cathode, it gains 2 electrons to become a normal atom. So when any ion goes to cathode or anode, they have to become a normal atom again. And with bromine as well, Br minus needs to become normal Br, so it will gain an electron. So they'll gain or lose electrons depending on whichever they need to become a normal atom. So normally it's easy to tell, right? So a positive metal will go to the cathode, the negative non-metal will go to the anode, everyone's happy. But in the case of an aqueous solution, there will be some differences. Like if you look at this case, chloride will end up going to the anode, that's normal, right? But instead of sodium going to the cathode, it's hydrogen. So you need to know if it's an aqueous solution, the cathode will always be hydrogen unless your metal is less reactive than hydrogen. For example, if we had copper would go to the cathode because it's less reactive than hydrogen. So number one priority is hydrogen. If there's anything less reactive, that will go there instead. In the case of the anode, oxygen will always be formed there, unless you have a group 7 element. In this case, chlorine is a group 7 element, so it gets released there. And you can see in these other examples as well. So this one has chlorine, therefore it gets released in the anode. And over here, because it's copper, and copper is less reactive than hydrogen, it will end up at the cathode. Again, with the third one, the anode is oxygen. This is because there is nothing in group 7 here, so it will always should be oxygen. The cathode is hydrogen, because there is nothing less reactive than hydrogen. The main one to remember that's less reactive than hydrogen is just copper, to be honest. It's a copper or gold. And last one, this sulfuric acid. Again, oxygen is released because there's nothing in group 7. And as for the cathode, hydrogen is released because there is no metal that's like less reactive than hydrogen. So there's no copper or anything. So in general, just keep an eye out for that. So if it says molten, just do it normally. Metal goes there, no metal goes there. But if it says aqueous solution, so anything about solution, you have to do that whole way. So check if it's less reactive than hydrogen and check if it's a group 7 element. The last case you need to know about is here when you have a copper solution, but you also have copper cathode and a copper anode. So what do you expect to go to the cathode in a copper sulfate solution? Well, we check, right? Is it less reactive than hydrogen? Yes, copper is less reactive than hydrogen. Therefore, the copper will go to the cathode. The thing with the anode, and this is just a specific case for its copper electrodes, the copper in the copper anode will go into the solution. So it kind of replaces the copper that went to the cathode. So the equations would be, in this case, for example, the copper ions in the solution, so Cu2 plus, go to the cathode and become normal atoms. So how can copper 2 plus become a normal atom? Well, it needs to gain 2 electrons. So it'd be plus 2 electrons there. And this should make just normal copper. And at the anode, the opposite is happening. We have copper atoms becoming copper ions. So it's becoming part of the solution over here. So it'd be copper becoming, so just literally backwards, copper 2 plus. Okay, it's really hard to write, but copper 2 plus 2 electrons. So you can ask you about this specific case where if you have copper electrodes, the coppers in the solution should go to the cathode and it'll get replaced by the copper in the anode. So relative formula mass, or MR, is when you add up the mass numbers for each thing inside of your compound. For example, H2O, the MR is just 2 hydrogens and 1 oxygen. Just add that up and you should get 18. So empirical formula is the simplest ratio of atoms in a compound. So a typical question would say something like 10 grams of hydrogen and 80 grams of oxygen, or could even be like 20% of hydrogen or 80% of oxygen. Whatever, it's the same kind of thing, doesn't really matter, the same way. You must first find the moles of both those things. And here comes the most important equation of all time when it comes to chemistry, which is moles. Again, this is hard to write, but equals mass over MR. So you should know the MR of hydrogen is 1. The MR of oxygen is 16. So how can you calculate the moles for each one? Well, for hydrogen, it'll be 10 over 1, which is just 10. And oxygen will be 80 divided by 16, which is 5. And you want to find the simplest ratio of that. So in this case, it would be 2 to 1, right? So your answer should just be H2O. This is how you find the empirical formula of anything. This is like a typical 4 or can even be 5-mark question that's generally always asked in chemistry questions. And it is this. So they'll give you the mass of, in this case, magnesium. They can use 6 grams of magnesium. and they're asking you to find out how much magnesium oxide is made. So how much of this is made. So first thing you always want to do is, they give you the mass, you have to find the moles yourself. So, if you go over to the periodic table, you'd find that magnesium has a MR of 24. So the moles of magnesium is the mass over the MR. So it's 6 over 24, which is 0.25 moles. 0.25. So that's the moles of magnesium. Once you found the moles of one thing, you can find the moles of anything in your entire equation just by looking at the big number in front. In this case, the number in front is 2. This tells you the ratio of their moles. For example, oxygen here will have half the number of moles because the ratio here is 2 to 1 if you just look at the big numbers in front. But we're trying to find the magnesium oxide. So because there's 2 in front of here and there's a 2 in front of here as well, that means they have the exact same number of moles. So you'll get 0.25 moles of magnesium oxide as well. And the questions ask us for mass. So again, we use the trusty equation, the same one we've been using this whole time, which is moles is mass over MR. I hate writing this, but that's life. So to find mass, we can multiply our moles by our MR. So 0.25 times the MR of magnesium oxide, which is 40, I believe, if you add up. So 24 plus 16. So it'd be 40 times 0.25. So your answer should be 10 grams. The last thing about moles is, the actual definition of moles. So 1 mole is 6.02 times 10 to the power 23 atoms. So in this case, it says, how many atoms are in 0.01 moles? Well, you'll do 0.01 times that 6.02 times 10 to the power 23, that whole thing. So that number is just how many atoms make up 1 whole mole. So here's the reactivity series. Obviously, you don't need to remember it, but you should have a decent idea of what it looks like. So the ones at the bottom are silver and gold. So you can find these metals underground in their pure forms. They're not going to be reactive. It's not going to be like a compound like gold oxide or silver. They are very unreactive, so you'll find them pure. The ones over here, they're going to be found as an ore, which means you'll find iron oxide or zinc oxide, but you won't find pure iron or zinc. So we need to do a displacement reaction to remove iron from iron oxide. And generally, that's by using carbon. So if I reacted carbon with iron oxide, because carbon is more reactive, it will displace the iron and become carbon dioxide plus iron. So this only works for things less reactive than carbon. We can use carbon to displace them. So we can actually just extract the metal on its own. Anything above carbon, we're going to have to use electrolysis. When metals displace each other, that's an example of a redox reaction. Redox just means both reduction and oxidation is happening at the same time. And again, the acronym you need to remember is OIL-REG. So oxidation is the loss of electrons, reduction is the gain of electrons. Another method of extracting metals is called phytoextraction. This is when you plant a plant in an area that has, a lot of metal. The plant will then absorb the metal. You then burn this plant, and the ashes should contain a high percent of that metal. And lastly, we have reversible reactions, which are reactions that can go both ways. So you should know that if one way is exothermic, the other reaction is endothermic. And the ways we can affect equilibrium. So we can affect again, it's a reversible reaction, right? It'll go both ways, but sometimes we want more, let's say, of the product instead of the reactant. So the 3 things you can control are the temperature, the pressure, and the concentration. Increase in temperature will shift equilibrium to the side that is endothermic. And the opposite will happen if you decrease temperature. Increasing pressure will shift equilibrium to the side with fewer molecules. And lastly, increasing concentration of one side should shift equilibrium to the opposite side. The example that you need to know is the Haber process. So that's when you react nitrogen and hydrogen to produce ammonia. So the equation for that is N2 plus 3H2 makes 2NH3. The Haber process is an exothermic reaction. This means increasing temperature would shift it to the left because increased temperature should shift the end of like to the endothermic reaction. So a high temperature would actually end up making less ammonia. The reason why we still keep it at 450 is because you need a higher temperature just for the rate of reaction to be high. And again, with the pressure, our equation is N2 plus 3H2 makes 2NH3, right? So if you count up the number of molecules on each side, you'll see that, as again, I have to finish off writing this. So 2NH3. You'll see that there's only two molecules on the right side, and there's a total of four on the left side, right? We have three H2s and then one, this N2. So this tells us that there are fewer molecules on the right side. So increasing pressure will shift it to the right. And lastly, you want to use a catalyst as well, just to speed up the reaction. The reason why we don't make our pressure too high is because, it could be explosive if you use it at very high pressure. So it's just for safety reasons. Again, temperature. We should have decreased temperature to make it more NH3. But because temperature is needed for a fast rate of reaction, we kind of had to go in between. So 450 degrees is a compromised temperature. Generally, the question will always tell you which way is exothermic and which way is endothermic. And from there, you need to remember the three rules for Le Chatelier's principle. And this is something that will most likely come up. So you need to remember how temperature, pressure, and concentration affect equilibrium.